every single day. And I just wanna tell you I am.
About 2 more minutes. So make sure you do the seating chart. And you will need your eye clickers and you will need your best friend today. All right, so where does spaghetti go to dance? The meatball. So I have a few announcements before we start. I did post your grades. So your exam grades are posted. all of your homework scores are posted, and your most updated iClicker score is posted to Moodle. So all of your grades are as up to date as humanly possible as of this morning. So that being said, drop day is coming up, right? Drop day is November 30th. So if you are thinking about dropping, you should absolutely meet with me, and we can talk about it, but you won't have another exam before drop day. So you won't have a really significant change in your grade. I mean, we're going to get more iClicker points. You're going to have homeworks, absolutely, but you won't have another exam score before drop day. So this is a good evaluation for, you know, if that's something you're thinking about. I will bring the exams in for y'all on Thursday. So I'll have them for y'all on Thursday. Any questions about that? Because our next exam is like the 7th, I think, December 7th, right? And then we'll have the final exam. So we're getting close to the end, y'all. You could do it. We don't have much longer to go. Any questions? It's a good thing and a bad thing all at once, right? Yeah. And then remember that your lowest, once all the exam grades are in, your lowest regular exam score will be dropped. You will still see it on Moodle, but if you do the math and you average all 4, it's going to be lower. So if you want to know what it's averaging, you take the 3 highest exam scores, add them up, divide by 3, and that's your percent for exams. Okay. And you know, there's an exam calculator, a score calculator that you can download. So if you go here, final grade calculator, if you want to see what you would have to make on the last exam and on the final exam to make a fill in the blank with whatever grade you want, you can do that. But the thing is, when you click on this, you have to download it. You can't just go to the place on Moodle. You actually have to see the little download button. You have to actually download it. Otherwise, when you were typing in your scores, everybody would see that. So we're not going to do that. That's why you have to download it. Okay. All right. Any questions? Good. Okay. Let me close this. So y'all ready for iClicker? Let's do this. Okay. A single water molecule can make a maximum of blank hydrogen bonds. Remember this one, this part's by yourself. Please make sure those masks are covering noses and mouths. Everybody, noses and mouths. 1 minute. Okay, 10 seconds. Okay. Turn and talk to your neighbors. And you can chat on Zoom. Okay, it'll be 45 seconds. I'll shut it down. So make sure you click in for a second time. Okay, 5 seconds. All right, so what did we say? So it is D, it is D. And good, we went up. So when we look at this water molecule, this is a pretty good water molecule. Remember, I've been asking you to draw water molecules, right? This is pretty good, but I'm missing something. What am I missing on my drawing of water? I think I heard it. Charges. It's not full charges, it's partial charges. So there are a couple of ways that you could do that, right? What are some ways that you can write charges? So you can write the arrows. If you write the arrows, I would say, okay, this is a polar bond and oxygen's more electronegative. This is a polar bond and oxygen's more electronegative. So that would, I'd have to combine these two arrows and make one big dipole moment, right? So you could have that. You could have that. So this is one acceptable answer. What else? How else could I do that? I could say this oxygen is partially negative. This hydrogen is partially positive. This hydrogen is partially positive. It's saying the same thing. So why is water awesome? Because it's polar. It's polar. So how many hydrogen bonds can it do? 4. Where are the 4? Most people get these 2. We have a hydrogen attached to electronegative oxygen, right? These are called what? Donors. But those aren't the only 2. Y'all told me there were 4. So where are my other 2 sites for hydrogen bonding? The lone pairs. Each lone pair is an acceptor site. This is why water is so cool, because it is polar. And especially when we convert water from being a liquid to a solid, right? All of those hydrogen bonds have to be formed and they have to stay that way in a solid form. So the water molecules, when they're in water, they kind of move around each other, right? So they're kind of compact. But when water turns into a solid, because of all these hydrogen bonds, they actually get farther away and get stuck in their positions. So that's why ice floats in water. Y'all have no idea how insane it is. It's insane that ice floats in water. No other substance does the solid form float in the liquid form. None. It's crazy. Well, like she's crazy. Okay, it is 4. It is 4. Okay, so now using that knowledge, right? Which of the following solutes would you expect to dissolve in water? So what do you think is going to dissolve in water? Okay. Time's almost up. Make sure you click in. Okay. Turn and talk to the people around you and click in again. Remember on Zoom, you can chat on Zoom, 10 seconds. Okay. So what did we say? Very good, very good. It is C, and we did go up. Very nice. Okay, so remember, what's the rule? Like dissolves like. So what is polar? So what is polar? Oh my God. What is water? Water is polar. So polar substances will dissolve polar substances, right? So hexane is polar or non-polar? If you're hydrocarbons, all hydrocarbons are non-polar. So it can't be hexane. CCl4. Now be careful with this. Do I have polar bonds? I absolutely do. Chlorine is more electronegative. So I have all of these polar bonds. But tell me about these polar bonds. They all cancel each other out. And so you end up with, although you have polar bonds, a non-polar molecule. Okay. How about C? To keep your mask up when you cough. Okay. CH3, CH2, OH. The OH has lone pairs on it. So those are two what? Hydrogen bond acceptor sites. And the hydrogen is a donor. It's a donor. So we have 3 hydrogen bond possibilities here. So like dissolves like. This is a polar molecule, right? So this is polar. Yay, it's polar. How about pentane? Non-polar, it's a hydrocarbon. Okay. So you have to keep those characteristics of molecules in mind when we're talking today. All right, so let's close that. All right. On the wrong page, but that's okay. All right, so what we're going to do in chapter 8 is we're going to talk all about solubility. All about solubility. So when we talk about different kinds of mixtures, right? Let's scroll down. Just put yourself a place where you got some space to write. Yourself a space. Okay. What are the types? When we talk about something's going to dissolve in something else, right? Scientifically, that doesn't sound very good, right? It's not very explicit. So we always have a little bit of something, a little bit of something dissolved into a lot of something else. Right? So what is this little bit of something? That is the solute, and that is dissolved into the solvent. Who is the universal solvent? Is water. Okay. So I always think solvent is a V, and when I draw water, right, what does water look like? Looks like a V, right? Solvent, water. So that's how I remember solute and solvent. All right, so if we come up here and we say, okay, identify the solute and the solvent. So the solute is less, the solvent is more. Helio-X, a breathing gas. This is really cool. That is 79% helium. Do we normally have 75% helium in the air that we breathe? No, 79. It's 78% nitrogen usually, and 21% O2, and it's like 0.0005% helium. This is normal, yeah, normal air, right? So what's the big difference here? Nitrogen and helium. Look on the periodic table. What is the atomic mass of nitrogen? (14.01 AMU). How about helium? 4.00. Depends on how many 6 gigs they go to. So basically, one atom of nitrogen is more than 3 times the mass of one atom of helium, right? That's what that's saying. So if you swap the nitrogen and the helium, if you have 79% helium. The air is less dense, and therefore it's easier for someone to push the air in and out of their lungs. So if you have somebody who has difficulty breathing, you put them on Helio-X and they can more easily breathe. Because what gas actually enters the bloodstream? Oxygen. Helium doesn't, nitrogen doesn't. So you put the right percent oxygen and you swap out the other stuff for something lighter, and it makes it easier for them to breathe. Isn't that cool? Okay, so we want to identify the whole point of this. I got on a sidetrack. It's the solute and the solvent. So for A, what is the solute? Oxygen. What's the solvent? Helium. If we were in normal air, what would the solvent be? Nitrogen. Children's Tylenol oral suspension containing 160 milligrams of acetaminophen per 5 grams of water. What's the solute? Acetaminophen, absolutely. Why? It's milligrams. There's 1,000 milligrams in 1 gram, right? So this isn't even a gram. This is how much of a gram? Divide by 1,000, so move your decimal place 1, 2, 3. So this is 0.160 grams versus 5 grams of water, right? So what's your solvent? Water, okay? C, we have a herbal remedy dissolved in alcohol. What's our solute? We'll say the herb because I'm running out of room. And then what is my solvent? So is water always the solvent? No. Most commonly it is, but it's not always. You have to actually look at the individual stuff. Okay, now we got to talk about the different types of mixtures, right? What are my different types of mixtures? I have a couple of them. Solutions. What else? Colloids. What else? One more. Starts with an S. Suspensions. Now, I separated these for a reason this way, because I want this column to be both solutions and colloids, so that we can make some similarities and differences. We can organize these. So tell me about a solution. How do I make a solution? I take a solute, I put it in a solvent, and what happens? Solute dissolves into solvent. Therefore, my solution must be what? Transparent. So give me an example of a solution. Salt water. What else? Coffee is one they gave. Now, what if I add milk to my coffee? Is it a solution? Why not? It's no longer transparent, right? It's opaque now. So now if I add water, if I add milk to my water, I now have a colloid. What is in milk that makes it a colloid? Proteins and fats. So contains small molecules that, I'm running out of room. I'll erase the milk and I'll rewrite the milk. That do not dissolve. So examples are proteins, fats, right? And our example was milk. So in a colloid, right, you have small particle size and you do not dissolve. So are you transparent? Not transparent. Okay. Here's the thing I want to ask you. If you leave your milk container in your fridge, right, on your counter, wherever, before you put milk on your cereal, do you need to shake up your milk? No. So not transparent and will not settle. Will not settle. Okay, so whether or not you dissolve or you are resuspended but don't settle, that makes you a homogeneous mixture, right? So if you don't have to shake it up, it's either a solution or a colloid. If you don't have to shake it up and everything dissolves, it's a solution, right? Okay. So homogeneous mixture, I would say uniform. So you define it uniform composition and will not settle over time. So if we spend all this time talking about homogeneous mixture, all this kind of stuff, tell me about a suspension. Is it homogeneous? No, it's heterogeneous. So guess what it will do over time? So it will settle over time. So why will it settle? What's the difference between a suspension and a colloid? The composition isn't uniform because things settle. So what makes something settle? Size. So molecule size, and this is the solute, is large, right? Because something heavy will do what? Will settle, right? So think about some examples of suspensions. Our blood, because like red blood cells are really heavy, really dense compared to some of the other portions of blood. And so they will eventually settle, right? Muddy water. Have you ever done in like high school in earth science or environmental science? Have you ever seen these? They're a tube. And inside the tube is everything that's in rivers, right? So it has water and then it has sediment of different particle size. And you shake it up and then you can put it on your desk, right? And you wait. And the first thing to settle are the really big pebbles and things like that. So they go down to the bottom. And then you go, as you go up, the size of the particles get smaller and smaller. And if you leave it for long enough, the water becomes clear again. Have you seen those? Those are really cool. Same principle, right? Okay. Got off track again, but that's okay. All right. Identify the following as solutions or colloids. So are we going to have any suspensions? No. Okay. 5% albumin, a protein IV replacement fluid. So this is a protein that is dissolved in water. Is that a solution or a colloid? Colloid. In electrolyte replacement IV fluid lactated ringer solution. What is an electrolyte? Salt, right? You know all those Powerade, Gatorade, there are 5 electrolytes in here. Do you know what they did? They added salt, some different kinds of salt, but they added salt. And you're paying a lot of money for that salt. And you don't really need it. If you're exercising, water's great. Unless you're doing like extreme things where you're losing lots of electrolytes, but most of us don't, right? So electrolytes are just salt, right? Because you have, what is salt? What's an example? NaCl. If I put NaCl into water, what happens? It dissolves and disassociates. It's 2 different things. What is the disassociate? You remember when we talked about putting water in and the water interacts with the positive and negative ions, and what happens? You get Na plus Cl minus. Yeah. So that's a disassociation. That's what electrolytes do. You can have things that dissolve that are not electrolytes, but electrolytes must disassociate. Yeah. Okay. So I'm sorry, solution or colloid? It actually told you, right? Solution. D5W, a 5% dextrose IV fluid. So what is dextrose? Ose. What is an ose? A sugar. Is sugar polar? Will it dissolve in water? Yes, so this is a solution. Okay. All right. So now we need to talk about when we make solutions, what are the parameters of that? So I can add salt to water, right? And what's going to happen? I just told me it's going to dissolve and dissociate. But if I keep adding salt, I just keep adding salt. It's going to dissolve, it's going to dissolve, it's going to dissolve until I get to a point where what? It stops dissolving. I can keep adding salt, but no more is going to dissolve. So what do we call that? A saturated solution. You have put in so much solute that you cannot dissolve any more solute. So if you look at A and 8.6, a piece of rock salt that does not change size when added to a salt solution. What do you have at that point? A saturated solution. Okay. B, a teaspoon of honey that dissolves in hot tea. Is it saturated? No, it's not saturated. So no, not saturated. All right. Okay, so when we talk about solutions, let me come down. I want to get to some blank space. Okay. We can change the parameters of if something dissolves or not, right? You remember that pot of salt water that I had and I kept adding salt to it, right? And then it stopped dissolving. If I wanted to make that salt dissolve, what would I do? I'd increase the temperature. I turn the heat on, right? So anybody know how real iced tea is made? I'm talking real iced tea. I'm not talking no Crystal Light. I'm talking real stuff. What do? You boil water, and in your pitcher, you put your tea bags, and you take the water off. So the water is super hot. It's not boiling, but it's super hot. And you pour that hot water over the tea bags. And while the water is still hot, what do? You add your sugar, right? Because if you add your sugar late, what happens? It's like gritty, right? It's not quite dissolved. So tell me what happens when I increase temperature what happens to the solubility of a solid, whoa, in a liquid? Up or down? Increase or decrease? We increase. And this example is for real iced tea. Right? Okay, now my next question is, what happens if I do the same thing, but now instead of talking a solid and a liquid, I'm going to talk about a gas in a liquid. Okay, so I'm changing this solid to gas. So this is my drink of choice, Diet Coke, right? So if I did this last period, I can't drink a whole Diet Coke in one class period, or I would have brought two, but I can't do it. When you pop the top, what do you hear? Right? Why do you hear that? It's pressurized, right? It's pressurized. Okay. So if you're living in Louisiana, we all know you do not leave your sodas in the car in the heat of summer. Why? They can explode. Why can they explode? What is in here? I have a liquid, right? What gas have I dissolved in here? CO2, right? So it's carbonated water. So the gas that's in here is soluble in the liquid. Now, if I increase the temperature, do I increase the solubility of the gas and put more gas in the liquid, or do I decrease it and more gas escapes? You decrease it, so more gas escapes. Now I have more pressure inside of that can. What happens? It explodes in your car. It's gross, right? So as I increase temperature, what happens to the solubility of the gas? It decreases. Let me talk about that going the opposite direction, right? Of a gas in a liquid. Okay, let me talk about it another way, right? I opened this can last period. By the time y'all leave, and I can sit and enjoy my Diet Coke, how's it gonna taste? It's 3 hours later, flat, gross, right? Why? Okay, what could I have done? If I was really smart, I would have popped the top, showed my class, ran to my office and put it in my refrigerator. Why would I want to put it in my refrigerator? Because if I lower the temperature, the gas remains more soluble inside the liquid and it still tastes good 3 hours later. So as I decrease the temperature, what happens to my solubility of my gas? Increase. So this is my Diet Coke in the fridge. This is my Diet Coke in a hot car, right? Oh, that is terrible, right? You can equate solubility of liquids and gases into other liquids, remembering iced tea and Diet Coke or regular Coke, you know, whatever floats your boat, right? If you remember those two examples, you automatically know these things. You just have to connect them to the right vocabulary, right? So let's go try to do that. Scroll up. All right. So if the temperature of a solution decreases, the solubility of a gaseous solute will. Are we talking Diet Coke or are we talking iced tea? Diet Coke, right? That's my CO2 in my Diet Coke. So if my temperature decreases, that means I put it in the fridge, the solubility will increase. I'm just going to put it up arrow, increase. I'm telling you, y'all going to be thinking on the exam of me and my Diet Coke, and you're going to get the correct answer every time. I know it. If the temperature of a solution decreases, The solubility of a solid solute. What is this? This is my sugar in my iced tea, right? So if I increase the temperature, what happens to the solubility? I increase the solubility. Yeah? All right. If the pressure above a solution decreases. So let's talk about gas and pressure. Which one did I say? What did I say? Decrease, which one? The solubility, if the temperature of a solid, oh, the temperature decreases, this decreases. I was reading, I think I said increase. Sorry, y'all. Right? If the temperature goes down, the solubility goes down. I think I said it. Okay, so my Diet Coke, right? They packaged this Diet Coke under pressure, right? Because you know that because when you pop the top, you hear that psh, right? So if Coke manufacturers did not produce this product under pressure, would you have a carbonated beverage? No, you would have a uncarbonated beverage. It would just be like a sweet, super flat drink, which sounds really gross, right? So if we decrease the pressure above a solution, which means if I take this Coke and I release all of the pressure, I leave it sit out, what happens to the solubility of the gas? If the pressure decreases, the solubility decreases, right? Because if I release the pressure, that's just what I did when I open this top and I leave it out. Eventually, all the gas is going to come out, right? But if I don't pop the top and I go put it in my office, I could come back a year later and it's still going to be fizzy, right? All I did was change the pressure when I open this. When I open this, I decrease the pressure over the solution, right? Therefore, the solubility will decrease. So this is my, if you open a can of Coke, right? A was Diet Coke, you could say Diet Coke in the fridge, right? Okay. So now let's talk about some other situations. Explain what's happening in the situations in terms of solubility. So fish die in a lake that is heated with water from a power plant cooling tower. This happens all the time. It's very, very bad for the environment. So why are the fish dying? As temperature increases, what do the fish need to survive? Oxygen. So as temperature increases, what happens to the solubility of the gas? Solubility of O2, which is a gas, in the water does what? Decreases. So fish have less to breathe, right? So basically you're suffocating the fish. And fish can't breathe. We'll put breathe, right? Because it's really gills, not lungs, but you know what I mean. So you have less O2 in the water. That's a problem. And that happens all the time. Okay, crystals form in a jar of honey that has been sitting for several months. I have my jar of honey. I put it out. It's not closed, right? What happens? What is honey, basically? Sugar. Particular kind of sugar, but basically sugar and water. Basically. So if I put this out on the table, what is going to happen? If I put a bowl of water out on the counter and I come back a week later, is the bowl still full of water? Why not? It evaporated. So if I put out honey on the counter for a month, what's going to happen? Water will evaporate. Water is the what? Solvent. So I'm going to lose solvent. When I lose solvent, what's going to happen? I'm going to create more solute. What do we call that? When things start to not dissolve anymore? Saturated. So causing a saturated solution. Once things saturate, right, they don't dissolve anymore. So that's the crystals. Yeah. All right. A person receives oxygen through a breathing device. There are two kinds of breathing devices. Let's talk about just a nasal cannula, right? You've seen that before? So what's in there? What gas is in there? Oxygen, but don't we breathe oxygen? So how is it different than what we breathe on a daily basis? It's more concentrated. Now be careful. When we talk about gases, we don't really say concentration. It's true, but we say partial pressure to say it's a gas. So anywhere where you hear partial pressure, I want you to think concentration of a gas. It's the same thing. So partial pressure is the same thing as concentration of a gas. It's the same thing. All right, so if you receive oxygen through a breathing device, right, the nasal cannula will increase the concentration, and I'll put / partial pressure of O2, right? So the higher percent O2 you're breathing, the easier it is for you to exchange CO2 for oxygen. That's one type of breathing device. What's the other type of breathing device? A ventilator, right? What does a ventilator do? It forces air into your lungs. If I'm forcing, that means I have a higher pressure, not a partial pressure, but just an overall higher pressure. So, or you have a higher pressure air, right? Either way is going to get you to breathe more efficiently. Okay. All right. So now, if you are in the unlucky situation that you have been exposed to carbon monoxide, what is the formula for carbon monoxide? CO. Do we make CO? No. What do we make as a byproduct of cellular respiration? CO2, right? So our bodies know how to handle carbon dioxide, but not carbon monoxide. So here's the problem. Your red blood cells are filled to the brim with hemoglobin. Hemoglobin is a molecule that can bind to 4 oxygen molecules at once. Your red blood cells are so devoted to hemoglobin that they even degrade their nuclei so that they can hold more hemoglobin. I'm telling you, they are dedicated. So the whole point is when you breathe in, right, your red blood cells will pick up O2 in the hemoglobin and then transport it all over your body, drop it off at your tissues, pick up CO2 that you made in cellular respiration, take it back to the lungs, and exchange again, right? So what happens with carbon monoxide is that carbon monoxide will bind to the hemoglobin with a much, much, much higher affinity than oxygen. So even if there's oxygen around, your red blood cells would prefer to bind carbon monoxide. So you can have carbon monoxide poisoning even if you're only exposed to a little bit of carbon monoxide. That's why we have carbon monoxide detectors in our houses, right? So in order to treat somebody who has been exposed to carbon monoxide, we put them in what's called a hyperbaric chamber. A hyperbaric chamber contains 100% oxygen. We normally breathe what? 20%. So what you have to do in order to get the carbon monoxide out is to outcompete for the binding sites on hemoglobin, right? So by increasing the percent of oxygen, this is really a concentration thing, right? So what did we do? We increased the partial pressure of O2, right? If we increase the partial pressure of O2, now the O2 will outcompete carbon monoxide, CO, for binding to hemoglobin. Which is in the blood, right? And that's Henry's law. Henry's law is all about partial pressures, but you can really just think about it as concentration. Right? So you have to give those red blood cells no other choice. The only thing that they can do is swap out with oxygen. Okay. Now, we're going to talk about solutions, and we're going to talk about them in general and how they dissolve and things like that. And then we're going to talk about them in terms of what do you give a patient and why is that important? Okay. So when we first talk about solutions, you have to understand that not all substances dissolve in the same way, right? So we have the word dissolve, and we talked about disassociate, right? Are they the same things, dissolving and disassociate? No, they're absolutely not. Okay. In order to dissolve, what are your requirements to dissolve? Yeah, you have to have a solute, right, into a solvent. And you have to have similar characteristics, right? So if I have, for example, NaCl in water, right? The NaCl, this is what? Ionic, so it is charged. Water is what? Polar. So what kind of interactions can happen between the two? Ion dipole, right? Yay, they can dissolve. Woohoo. They can interact with one another. Can NaCl disassociate? So NaCl in water will dissolve and disassociate. Because when those interactions are made, when those ion dipole interactions are made, we're saying that ions are formed. So if I take NaCl and I put it into water, what am I going to get out? Salt water. That's Na plus Cl minus, and the way that I say it's in water is I put AQ. I say it's aqueous, right? But now tell me about sugar in water. Sugar is what? Polar. Water is what? Polar. So now we have what kind of interaction? Dipole-dipole, but in this case, we have the strongest form of dipole-dipole, which is hydrogen bonding. I would take dipole-dipole as a correct answer, but because hydrogen bonding is a type of dipole-dipole interaction. But now, so sugar and water will dissolve, but do I break my sugar apart? Right? This is my sugar. Does it change when I put it in water? No, I still have sugar. I just have this sugar that's making hydrogen bonds here and here and here and here and here, right? We got hydrogen bonding going on all over the place. But are we changing the composition of the sugar? No. So it will dissolve, but not dissociate. Right? So this is our illustration that dissociation and dissolving are not the same thing. So now, let's see if we can use some scientific terms in order to explain that. So if you have something that is a strong electrolyte, remember when we talked about electrolytes? Electrolytes do what? Form ions. That's the definition of an electrolyte. So a strong electrolyte will dissolve and what? Now it's strong, so it will completely, it will fully 100% dissociate in solution, in water. Right? Because you can also have a weak. A weak. A weak electrolyte, it's still going to be a weak electrolyte. It's still going to form ions, but it's not going to dissociate 100%. So it will dissolve and only partially dissociate in water. So how do we show that difference? In chemistry, we say if you have something that is XY and it fully dissociates, we draw a 1 arrow and it turns into X plus Y minus. Right? This is like NaCl. But you have some substances that are still ionic, but they don't dissolve completely. So what do? We're saying some of it still stays together. We do the back and forth arrow. Right? So some of it makes these ions, but some of it stays together. But they're all aqueous. Right? They're all aqueous. And you just put water on top, right? H2O on top. Okay, but that's not the only thing that can happen, right? You can have a third class of molecules. The third class of molecules is a non-electrolyte. A non-electrolyte will still dissolve, but will not dissociate. So how do I draw that? How do I write that in chemistry? It stays the same, So usually it'll tell you what state of matter you start as. So usually it's a solid, and we're going to put it into water, and it's going to become aqueous. Did the formula change? No, because it didn't disassociate. So we leave that formula the same, we just change the state of matter. Okay, you feel like tackling some of these? I think we could do it now. All right, where were we? Oh my gosh, I went so far down today. Jeez. Okay, so, oh, but it's on the next page. Haha. Okay. Predict if the following will fully disassociate, partially disassociate, or not disassociate when dissolved in solution. Sodium sulfate, a strong electrolyte. If it's a strong electrolyte, what should it do? Fully disassociate. Ethyl alcohol, a non-electrolyte. It will not disassociate. Will it dissolve? Absolutely, but it will not disassociate. Hypochlorous acid, a weak electrolyte. Partially. Right, once you know those definitions, it's easy. But now the next step is going to be to write the chemical equations for these reactions. So if you go down, the very next thing, provide a balanced equation for the hydration of each compound. So A, Na2SO4 solid. Now, there are two ways to write this, and I want you to recognize that they are the same thing. I could put plus water here and then draw my arrow. Or I could write Na2SO4 solid. Oops. Put my arrow and put water on top. It means the same thing. So your book tends to use the one at the bottom, and that's fine. I just want you to understand it's the same thing. Okay, so this is an ionic compound. It's a strong electrolyte. If this is a strong electrolyte, what is this part of the compound and what is this part of the compound? I have a metal and a polyatomic ion. So now you need your best friend, right? Because you have to go find charges for these two things. Where would I find the charge for Na? Periodic table, right? So Na, we're going to disassociate it. It's going to be aqueous. But because it disassociated, now you see the ion, you see the charge of the ion. So what's the charge of Na? +1, but we don't really write the one, we just write plus. Now, you could look at the formula and know what the charge is of your polyatomic ion, or you could do what? Go find your polyatomic ion table and go look up SO4, make it aqueous because it's dissolved, and tell me what the charge is. -2 or 2 minus. Please make sure those masters still cover noses. Okay. So how could I have done this just by looking at the formula? Because sometimes you're going to have to do this. You remember our crossover trick to write formulas? Now you would just do the reverse crossover. So I would see that this 2 here would mean that this SO4 is a 2 minus. And then I would have to know that this SO4 is a polyatomic ion. So it's actually in parentheses and it has a 1, but we just don't write the 1 in the parentheses. So that 1 would tell me my sodium is a +1. Yeah, because you're going to have to do that in the future. Okay, so now I'm going to erase this just because I have so much going on. And I want to ask you something important and not have all that going on. Na2SO4. If I write a chemical equation, it must be what? Must be balanced. Are we balanced? No. What do we do? add a 2 to the Na. Could I have put the 2 down here? Why not? That would be sodium bonded to another sodium. I can't just magically do that. I can only change coefficients. Okay. All right. B, ethyl alcohol. CH3, CH2OH. This is a liquid. We're going to put it into water. What are we going to make? The same thing. This is a non-electrolyte. Your chemical equation won't change. But what does change? The state of matter goes from a liquid to being aqueous. That is the only thing that changes. Very nice. So are we balanced? If you didn't change the formulas, you're balanced. That's the easiest ones. Okay, C. What is C? Hypochlorous acid, HClO, AQ. And we're going to put it in water. Okay, this is a weak electrolyte. So what do I have to do with this? I got to do the two-sided arrow. Now, an acid. What happens when an acid gets put in water? Anybody know? We're going to disassociate, right? This is a weak electrolyte. By definition, it disassociates. So what comes off, right? For an acid, disassociation of an acid means the hydrogen leaves the molecule. Okay, so if disassociation means the hydrogen leaves the molecule, if I take this and I separate the hydrogen from the rest of it, that's all I did. It was neutral before. Can the two pieces be neutral? No. So to answer what's the charge on the hydrogen, I want you to go look at your polyatomic ion table, because this, the thing that an acid is, the acid is a hydrogen plus a polyatomic ion. So go look and find ClO. What is ClO? It's a -1. So if my charges have to be balanced, what's my charge on hydrogen? It's a +1. So now I just make it aqueous, make them both aqueous. Am I balanced? Yes, I am. Okay. Not too bad, right? Okay. For the following ionic compounds, hint, 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 it's ionic. So we're going to assume these are all solids. Just assume they're all solids. We're going to write a balanced equation for their hydration in water. And we're going to assume not only are they all solids, but we're going to assume 100% disassociation. Right? So A, FeCl3. I'm going to assume it's a solid. And I'm going to assume 100% disassociation. So what should I draw? A single arrow. Now, I'm always going to tell you, the book doesn't tell you, but I'll always tell you. Okay. What happens? My iron is going to separate from my chlorine. They're both going to become aqueous. Do I know the charge on iron? It's a transition metal. Uh-oh, SpaghettiOs. Yep, I got to do my reverse crossover. So what's the charge on chlorine? -1. So what I'm going to do is I'm going to do my reverse crossover, and it's okay as long as chlorine gets a -1 when I do the crossover. Otherwise, I'm going to have to multiply. So I assume that this is a 1, right? If nothing's there, I assume it's a 1. So I do the reverse crossover. So that becomes -1. So that's great. Perfect. Now I'm going to take the 3 on the chlorine and turn that into +3 or 3+. Okay. Now, can I erase the reverse crossover? I got that? Because I don't like to leave it because we have to look at some other things. So am I done? Why not? I am not balanced. What do I do to balance this equation? I put a 3 in front of the chlorine. All I can do is change coefficients. It's the only thing you can do when you balance chemical equations. Okay, B. NaHCO3, we're going to assume it's a solid. We're putting it in water. What happens? Go look at your polyatomic ion table. Do you find something? What do you find in your polyatomic ion table that's in this substance? Hydrogen, carbon, carbonate, so HCO3. So I'm going to make HCO3 and Na. How do I know my charges? Do I have to do the reverse crossover? No. I could go to the periodic table for Na. What is Na? +1. What is HCO3? I can just go to my polyatomic ion table. -1. So these are both aqueous. And what are we balanced? Yes, we are balanced. We are good. Okay. C. K2SO4. So I'm going to assume it's a solid, and I'm putting it in water, and it's going to disassociate 100%. What happens? What do I make? I make potassium, and I'm going to say it's aqueous, and then I make my polyatomic ion of SO4. And it's aqueous. So go on your polyatomic ion table, go find SO4. What is SO4? -2 or 2-. So now, what is potassium? It's a +1. Am I balanced? No, I'm not. What do I need to add? 2 in front of potassium. So far, so good. I'm going to erase A and B to fit in D. Okay, is that all right? And I assume so. Okay. All right, so we got D. CaNO3 2. It's a solid. We're putting it in water. What's it going to disassociate into? Ca, and that is a aqueous, plus NO3, and that is aqueous. What are my charges? Calcium, I can look on the periodic table, is a 2+. NO3, I can go to my polyatomic ion table, and I get a charge of what? -1. Am I balanced? No. What do I do? I put a 2 in front of the NO3. So the way that you can do this, like I don't have to go and count individual atoms. If I go and I say, okay, I have the same number of calcium atoms and calcium atoms. But when I come over here and I go, wait a minute, right? This subscript 2 is telling me I have 2 of these polyatomic ions. But before I balanced it, how many of the polyatomic ions did I have? 1. So how do I change that? How do I get 2 of the same polyatomic ions? I just put the 2 as a coefficient. So do you have to go in and do each individual atom? No, this is a short and sweet, right? It'll work. If you do the atoms, it'll work. Don't get me wrong, but I'm just trying to save you some time. Okay. Now, when we give patients IV fluids, there are a couple of things that we have to worry about when we give them fluids. Number one, we have to worry about the concentration of ions that we give them. It has to be the same as what's normally there. Why is that? If I have a red blood cell, and that red blood cell has a particular number of charged particles inside of it, and I give a patient an IV, and that IV has lots of charged particles in it, what is going to happen? Can I open the door and let him out? It's a wasp. Just leave it alone and it'll leave us alone. What is going to happen? What happens? If I put this red blood cell in a concentration of a solution with a high concentration of charged particles, what happens? The water, ions can't move because they have to go through channels, but water moves freely. So the water is actually going to leave, water leaves the red blood cell. What happens to the red blood cell? It shrivels up and it dies, right? This is why you can't drink salt water. If you're stranded on a desert island, do not drink salt water. Collect rainwater, collect dew, anything, but do not drink salt water because it will dehydrate you. Drinking salt water will dehydrate you. Isn't that crazy? But it's true. Okay. The opposite is true. You have a red blood cell and you have that same number of particles inside your red blood cell, and I give you an IV that has fewer particles. What is going to happen? Water is going to go in. What happens when too much water goes into your red blood cell? It swells and it'll explode. So how important is the concentration of ions in IV fluids? Like super insanely important. So that's part of it. Now the other part of it is that we have to make sure that the charge is the same. Your body works on things that are charged. So however many positive charges and however many negative charges, we have to keep that balanced. So when we talk about the charges, right, we're not just talking about concentration. We're talking about if you have something that is Mg2+, how many charges are present on Mg2+? I have 2 positive charges. If I have K+, how many positive charges do I have? 1 positive charge. So it would be 2 positive charges per atom, right? So does it matter if I give a patient a solution that has Mg2+ versus a solution that has K+? I might give them the right concentration, but do I give them the right charge? No, not necessarily, right? If I give them K+, maybe I don't give them enough charge. Or if I give them Mg2+, I give them too much. So the way that we talk about this is with equivalence. Oh, I'm trying to erase. Hello. So when we talk about that, what you do is you look at the ion, and in this case, it's Mg2+. So we can write this, this conversion factor that says if we have 1 mole of Mg2 plus, I have 1 equivalent charge, not 1, hello, after I just said all that, we have 2 equivalent charges, right? Because it is 2 plus, we have 2 equivalent charges with Mg2 plus. Does that make sense? If I had K plus, right, like I have up here, if I have K plus, if I have 1 mole of K plus, I have 1 equivalent charge, K plus. So that way I can figure out how much of a charge I'm giving my patients, right? Okay, so how many equivalents of Mg2 plus? That's just saying like how much charge is present in a solution that contains 2.50 moles of Mg2 plus. So what do? I want to go to equivalents. So I got to put moles on the bottom. I just said here my relationship. I have 1 mole, 2 equivalents. So what do I get? 2.5 times 2 is 5. And make sure you put your significant figures. 3 sig figs, 3 sig figs. Equivalents, Mg2 plus. Right? Okay, let's do another one. We have a 5% dextrose IV fluid. It has 35 milliequivalents of K plus per liter of solution. If a patient receives 235 milliliters of the IV solution, how many moles of K plus were delivered? What do you want to start with? Okay, so 235 milliliters. Where do we want to go? We want to go to moles of K plus. So can we get rid of milliliters? I know I'm going to have to put it on the bottom. So let's put it on the bottom. Do I have anything in the problem that has milliliters in it? But I do have something that has what? Liters. So let's convert milliliters to liters. I know I have 1,000 milliliters in 1 liter. So my milliliters will cancel. And I'm going to put liters on the bottom. So give me my conversion that has liters in it. I have 35 milliequivalents of K plus per 1 liter of solution. Okay, so now my liters cancel. I'm in milliequivalents. Do I have something in the problem that will give me milliequivalents? This is just like milliliters. I got to get rid of milliequivalents. Right? A milliequivalent is the same thing as a milliliter, it's the same thing as a millimeter, it just means 1/1000, right? So I have 1,000 milliequivalents in 1 equivalent. So I get rid of my milliequivalents. I'm in equivalents, is that what I want to be? No. So do I have a conversion from equivalents to moles? Yeah, I do. It's not explicit in the problem, but what do I know because of the definition of equivalence? I know because I have a K, this is a +1. That means I have 1 equivalent of K plus for every 1 mole of K plus. So what do you get? What do you get? Love that calculator sound. Awesome. Just awesome. something really small because I'm dividing by 2,000, not 2,000, by 1,000 twice. 8225. Okay, so, and my units are moles of K plus, but is that the correct number of sig figs? No, how many sig figs? 2. This is my lowest number of sig figs that I used in my problem. So I need to go 0.0082 moles of K plus. Yeah. Perfect ending. Pick up on 8.4 next time. And I'll have exams for y'all next time as well. Anybody on Zoom need anything? All right, have a great rest of y'all day.